All right, so tonight we're going to go over chapter 7. And this is going to be over the concept of energy and then work. Generally, you're going to want to focus on the concept of energy before you get to work, because energy is usually defined as the ability to do work. So in order to be able to figure out what work is, you need to have an operating definition of what energy is. So energy is going to be exchanged and transformed during interactions of systems, but the total amount of energy in a closed system is going to be constant. So it can change from one form to the next, but it's all going to be contained within the system. So this chapter, we're going to look at three types of energy. Or three types of mechanical energy. We're going to have kinetic energy, which deals with objects that are in motion and that also have mass. We're going to deal with gravitational potential energy, and that's associated obviously with gravitational interactions, and then elastic potential energy, associated with elastic deformations of objects. And potential energy can be viewed as a stored quantity that represents the potential for doing work. So the definition of kinetic energy is really the main focus here that I want us to concentrate on. So an object with mass m that moves with a speed v has an intrinsic energy of motion called kinetic energy, and it's denoted by K, and it's going to be 1/2 mv squared, and the units are going to be in joules. Energy is going to be considered a scalar. It's not going to have a direction. Also, you cannot have negative kinetic energy. So it's either going to be positive or it's going to be zero. The kinetic energy can be transformed to other forms of energy, and it can come from other forms of energy. So let's say you've got two soft deformable objects, such as a couple of balls of putty or chewing gum. When they come together, we find that the kinetic energy is not conserved, but the bodies become warmer. And that's because there's a rise in temperature and a loss of kinetic energy. This new quantity, internal energy, that increases with temperature is a definite way that the sum of the kinetic energy and the internal energy is conserved in the collisions. In other words, the energy has changed its form from kinetic into internal energy or heat. So those are the kinds of things that we'll think about going forward. There's energy associated with heat, elastic deformations, electric and magnetic fields, and according to the theory of relativity, even mass itself. Newtonian mechanics is going to have limitations. It doesn't work for very fast motion. It is very good for a lot of the things that we see here on Earth. When you start trying to approach certain speeds, then that's when you start to see it break down a little bit. So if you're looking for very fast motion, you're looking at the theory of relativity. If you're looking at atomic or subatomic systems, that's when you're going to need quantum mechanics. But the concept of the conservation of energy, in other words, it's not, what am I trying to say here? The fact that energy is neither created nor destroyed, it's going to hold even in those types of systems. We don't find an exception for it. So here we're going to look at forms of mechanical energy, the energy associated with motion, position, and deformation of objects. We're going to find that in some interactions, mechanical energy is conserved, and in others, there's a conversion of mechanical energy into other forms, and we'll look at that later on. So Other classes of mechanical energy are going to be energy that is not directly associated with motion, but rather is that quantity that is stored as a result of the position or elastic deformation of an object. So let's say we've got a little bean shooter here. We have to expend energy to stretch it back. As soon as it's released, the physical changes start to occur, so the slingshot projectile flies across the room. An unstretched rubber band lacks that capacity. So how do we model that? The act of stretching the rubber band stores energy in it, and releasing it allows the stored energy to be transformed into other kinds, such as kinetic energy. So the stored energy is going to be referred to as potential energy, and then the energy that is stored in the elastic object when you stretch, compress, twist is going to be called the elastic potential energy. Another type of potential energy is going to be like a skateboarder. When the skateboarder comes off of the edge and goes down the half pipe, speeds up and gains kinetic energy. When he stops at the top of the opposite edge, he's no longer in motion, so he doesn't have any kinetic energy. But as soon as he comes back down, then he gains kinetic energy as gravity pulls him downward. So you can see how the energy changes forms. As he's up here, it's all potential energy. Down here, kinetic. Back up here, it's potential again. And that is all due to gravity. So, what is the entity that goes from object to object or from one form to another that is analogous to energy? And the answer is money. Money is going to take many forms, coins, bills, Bitcoin, what have you. You can store it, you can spend it. Even though it's real, it's also got a sense of a pure abstraction. So it's not only an abstract idea, but it also is a very real quantity, depending on how you look at it. So you can see here in this particular diagram, you've got energy of the elastic band as it's being released. That potential energy turns into kinetic energy for the rock. As it travels upward, its energy starts to be converted into gravitational potential energy. You can see its motion there as it quits moving, that all of its energy has been put into potential energy, and then as it falls, then it goes back into kinetic energy form. So here's another example where you've got a block that is right here before sliding. You've got all of these little atoms and molecules in here that are vibrating at room temperature. When you start to push it, then you've got friction that's bumping up against this, and that friction converts the kinetic energy of the sliding block into stronger atomic vibrations. So again, that's a transfer of one type of energy into another. So that's a lot of what this section is about. Any force that turns mechanical energy into non-mechanical forms is called a dissipative force because it reduces the mechanical energy of the system. Okay, so now that I've rattled on about that for a little bit, let's take a look at work. So when a force acts on an object and it undergoes a displacement, that force does work on the object and transfers energy to it. So if you have a constant force, that work is going to be equal to the force that's parallel to the object's displacement times S, which is going to be the measure of the displacement. The component can be positive, negative, or zero, and work is going to be a scalar quantity, not a vector. If the parallel force here opposite to the points opposite to the displacement, then the work is going to be less than zero. And when several forces act on an object, the total work done by all of the forces is the sum of the amount of work done by the individual forces, kind of like the way the components of the vectors work. So if you're looking for work done by a single force, and you're going to be interested in the direction in which it is parallel rather than perpendicular. So you've got this block and it's moving this direction. It moves a certain distance. And you take this times the cosine of it, which is going to be the vector or the component of the vector lying in the same direction as the displacement. So you take that force and you multiply it by the displacement. Okay, so let's say that, or let's start here. The importance of the concept of work stems from the fact that in any motion of a particle, the change in kinetic energy of the particle equals the total work done on it by the forces acting on it. So let's say all of our forces are combined here into one force on this object, pushing it in this direction. The displacement also happens to lie in that same direction. So the work is going to be the product of the magnitudes of the displacement and the constant force. So let's say we've got a car moving in this direction due to a force like this, say, wind, or some guy pushing or something like that. We can take that force and we can break it into two components, one pointed this way and the one pointed that way. Now, the car is actually moved in distance s in this direction. Also, if we take a look here, we know that we've got a component of the force that is in parallel with the displacement going in this direction. We also have a component here that is pointed in this direction, that's perpendicular. This part here does not do any work because there's no displacement in this particular direction. There's only displacement in this direction. So this is the component of the force that actually causes work to be done on the car. So again, this definition of work is if an object undergoes a straight line displacement with a constant force acting on it, and then the amount of force that's parallel to that multiplied by the displacement is going to give you the amount of work. So in a case like this, where you've got a force pushing this way, but the block is moving this way, the displacement is this direction, the force is this direction, they don't have any part or components of vectors that overlap. Therefore, there's no work done on that particular object by that force, even though it's in motion. So the units are in joules. Again, work is a scalar quantity that can be positive, it can be negative, or it can be zero. And if the object doesn't move, then there's no displacement. And because there's no displacement, there's no work. Also, if the force is perpendicular to the motion, then there's also no work done. If the sign of the work is positive, then energy is added to the system or object by the force. That would make sense. If the sign of the work is negative, then the force is removing energy from the system. So you can see you got several exercises here to go through. I'll just pick the first one. So we've got an object here that's mass m moving down a ramp. It's got a height of h and makes an angle beta with the ground. So we're going to find an algebraic expression in terms of these quantities for the total work done. So we go through here, draw a small diagram of what's going on. We know the displacement is this. We know it has a mass m. We know it was this high. We know the angle that it makes is beta. Go through the free body diagram here. We know we've got a normal force of the ramp pushing on the box. We see the angle of its displacement. We know that gravity is pulling on the box. We know that we have an x displacement this way, or an X component of the weight pointed this direction, we've got a Y component. So we can figure out what the magnitude is of all those particular items. So the work done is going to be F times sine of beta. And if you work on the trig there, you can kind of see how that part of it will come out. And that's going to be multiplied by the displacement in that direction. So when you multiply all of that together, as it turns out, the weight in this, or the work done in this case, is just going to end up being mgh. Since we're ignoring friction, which never got entered into this, the only force that does work on the package is going to be the weight. And so we found that the work is going to be the product of the weight and the vertical distance. This product is in fact equal to the gravitational potential energy at the top of the ramp. So work through a few more issues there, and they do have tutorials that go along with that and other problems. So. All right. Work and kinetic energy. So the kinetic energy of an object is defined in terms of the object's mass and speed. K is equal to 1/2 mv squared. When forces act on an object, the change in its kinetic energy is equal to the total work done by the forces acting on it. So we have forces that are doing work on the object, which means that they're adding energy to it. And one way we measure that is take whatever the kinetic energy is finally, subtracting what it was originally. It's going to be equal to that change in kinetic energy. If W is positive, then the object is going to speed up. If it's negative, it's going to slow down. So here we have apparently a Honda. It's got a mass of 1,300 kilograms. It's moving at 2 meters per second. Speed gets cut in half. What's going to happen to the kinetic energy? Here we came out with 2,600 joules. Here it turns out to be 1,300. Okay, so work and kinetic energy. You may remember, or you may not, the chapter that has all of your kinematic equations in it and how they all relate to each other. If we go through and we want to determine the force here, since we've got a particle moving along the x-axis under a constant force directed along that axis, the particle's acceleration is going to be F times ma. We know these relationships already, so we can determine what that is. And it turns out to be this. We take that and rearrange it a little bit. Then we find this particular arrangement. So the product of F times S, which we now know to be work, is going to be equal to this. That is just the difference in the kinetic energies. And so that's where this theorem comes from. So again, you have several problems there that you can kind of work through, get a feel for. Okay, not all forces are going to be constant as they work on an object. So if it is not constant, you can see a graph of the force, where it started out and where it ended up. And as x increased, how does the force change? It changes like this. So the work done by a force is going to be represented graphically as the area under a curve of the force as a function of displacement. So if the magnitude of force F requires to stretch or compress a spring a distance x from its natural length, and that's proportional to x, then F is equal to K times x, where K is going to be the spring constant. The total work needed to stretch a spring from 0 to x, or alternatively to compress a spring from 0 to minus x. this is going to be the amount of work you're going to need in order to be able to accomplish that. So, since you guys are in this class, you probably have not had calculus, correct?
No. Okay. I haven't.
Generally, for the 1600 class, that's what holds true. The reason I make that point is in calculus, you have ways of being able to calculate the area under the curve here using that particular method. But if you haven't had it, then you may not recognize that that's possible. So what we're going to do here is we're going to say, we're going to consider the straight line motion under the influence of a force that's directed along this line, but that it may change in magnitude as the object moves. So let's say you've got a particle moving along the x-axis from this point to this point, and the graph of the x component is a function of the particle's coordinate x. So to find the work, we divide the total displacement into little bitty small segments, and we approximate the work done by the force during each individual segment as an average force. So for this segment, we're going to say this is the average force. For this segment, we're going to say this is the average force. For this segment, we're going to say that this is the average force, so on and so forth until you get sick of it. So we're going to do this for each segment and then add all of it together. And then the work is going to end up being the sum of all of those products. So this is supposed to be a graphic demonstration of what's going on. You've got where you stopped or started and then where you stopped. We're going to take the height of each strip, and that's going to represent the average force for that particular interval. And that's what we turn around and we multiply by. So we're going to apply this analysis to the stretched spring. So to keep a spring stretched an amount x beyond its unstretched length, we have to apply a force at the end. If the elongation is not too great, then the spring is going to obey Hooke's law. In other words, F is going to be directly proportional to x, or the displacement. So K is going to be a constant called the force constant of the spring. 7.6 shows that the units of K or of force are going to be divided by distance. So a Newton per meter is what we're going to be looking at. So if you take this, rearrange it, divide both sides by X, you get newtons, which is the measurement of force, divided by meters, which is going to be the measurement of the displacement. So suppose that we apply forces with equal magnitude in opposite direction to the ends of the spring and gradually increase forces starting from 0. We hold the left end stationary, and the force at this end does no work on the spring. The force at the moving end does do work. So we're going to take a look here at figure 19. We've got a graph here of the x component of force as a function of x. And so the work done on the spring when the elongation goes from 0 to a maximum of x is going to be represented by the area under the graph. In other words, this is going to be x. This is going to be k times x. So the total work is going to end up being 1/2 of this length times that length. And that's what we get there. So it also says that the work is going to be equal to the average force multiplied by the total displacement. So that's another way of looking at it. The spring also exerts a force on the hand, which moves during the stretching process. The displacement of the hand is the same as that of the moving end of the spring. But the force on it is opposite in direction to the force of the spring because the two forces form an action-reaction pair. So in other words, the work done on the hand by the spring is the negative of the work done on the spring, namely this. So suppose that the spring is stretched at a distance x sub I at the start. Then the work we will have to do is to stretch it to a greater elongation. It's going to be defined as this. If the spring has spaces between the coils when it is unstretched, then it can be compressed as well as stretched, and Hooke's law will hold in that particular case as well. So let's say we've got a spring and it's stretched from x is equal to 0 to x is equal to 2a. Is more energy required to stretch the spring through the first half of the displacement or through the second half? In other words, does it require more energy to go from here to here or from here to here? So if we take it, we graph it. So Hooke's law is going to tell us that the force required to stretch a spring increases with increasing elongation. Thus, more energy is required to stretch the spring through the second half of the displacement. Another way to look at that is that if you plot the force against the x displacement, you're going to have more area going from A to 2A under the curve than you would going from 0 to A. So, potential energy. This can be thought of as stored energy. If you have an object with mass m and height y above a chosen origin, usually where y is equal to 0, the gravitational potential energy is going to be found by this formula. When a spring is stretched or compressed a distance x from its uncompressed length, something like this, then the spring stores elastic potential energy. In other words, if you take it and you squeeze it this way, you're going to put energy into it. If you take a book and you lift it up, you're giving it gravitational potential energy. And potential energy is only associated with conservative forces. What is a conservative force? A conservative force is one that is path independent. It doesn't matter how you get there. All right, so let's take a look here. So let's say you've got an object here, and this object is here, and let's say we let this fall. So we can see here that the distance above the ground here is going to be less at this point than the distance up to here. So the gravitational potential energy is going to decrease. In other words, your change in gravitational energy is going to be less than 0. You still have the weight of the object, so it's still being pulled there. This is saying, you know, you've got some of the force trying to push it up, or maybe work against it, maybe drag, something like that. This would be the way you would go about finding the change in the potential energy. And that's pretty much how it's represented. So let's say you have an object here that is being forced up. It still has the weight, but whatever force is pushing it up means that its initial distance above the Earth is going to be less than its final distance above the Earth. That means its gravitational potential is going to be greater. And generally, if you go through and if you define this level, let's say, as y is equal to 0, because you can set it to whatever you want, then you find out that the gravitational potential energy at that particular point is just going to be mgy, or whatever your distance is above that particular point. The work, the gravitational work that is done is going to be the difference in gravitational potential energy between the initial and the final. It's always going to be equal and opposite to that change in gravitational potential energy. So Let's say you've got an object moving along a straight vertical line. And let's say that the object's weight is the only force acting on it, so that any other force acting on it is zero. Let's say the object's in free fall, or perhaps we throw it up, what have you. So let the speed at y sub I be v sub I, and the speed at y sub f be v sub f. If we go through and look at the work energy theorem that says that the work is going to be the difference in the potential energies, in this case, the change in the amount of work added is going to be the amount of gravitational work, which is going to be where it started minus where it ended for potential energy. If you put all that junk together, you come up with this relationship. And if you move the I's to one side and the F's to the other, you find out that your kinetic plus your potential energy when you started out is going to be the same as the final potential and kinetic energy. Or another way of writing this, 1/2 mvi squared plus mgy sub I. And then the same thing over here, you're just dealing with F's rather than I's. So we're going to define the total mechanical energy, kinetic plus potential. And we're going to call that E. So this is going to be the total energy when the object is at position y sub I. And then you can see E sub F is going to be the sum of that. E is always going to be constant. It's got the same value at y sub I and at all other points during the motion. When other forces sum to zero, then the total mechanical energy is going to be constant or conserved. This is going to be a first example of conservation of energy. Several examples to go through there. Now, what about elastic potential energy? When you've got a railroad car that runs into a spring bumper at the end of the track, the spring is compressed as the car is brought to a stop. If there's no friction, then the bumper springs back and the car rolls away in the opposite direction. So during the interaction with the spring, the car's kinetic energy is stored in the elastic deformation of the spring. And something similar happens in a spring gun. Work is done on the spring with the force that compresses it, and then that energy is stored in the spring until you pull the trigger, and then the spring converts the stored energy into kinetic. So let's say you've got an object here that is stationary. The spring is neither stretched nor compressed. If you stretch it out, it does negative work on the block. In other words, you're decreasing its potential energy. If you were to push it in, you would be adding potential energy to it. The spring always does negative work on the block as it compresses. So your definition of elastic potential energy. So when a spring obeys Hooke's law, this is true. And when it's stretched or compressed at a distance x from its undistorted state, the associated potential energy is going to be given by this. That is a El Capitan, a mountain I will never climb. Not much into climbing mountains. So if we use equation 714 to express work done on an object by spring force in terms of the change in elastic potential energy, we can see the work here is going to be the change in the kinetic energy, change in potential energy, or minus the change there in the elastic potential energy. So when X increases, this is negative and the stored energy increases. And when X decreases, then you see the opposites happen. If the spring can be compressed as well as stretched, then X is negative for compression. So when X is equal to 0 and this is equal to 0, the spring is neither stretched nor compressed. So if the spring force is the only force that acts on the object, then total amount of work done on it is equal to the elastic work, which is the potential energy at the beginning minus potential energy at the end. In other words, total amount of energy is going to remain conserved. So that is a fairly big concept, and that's going to carry forward. I don't know, do either of you have plans to go forward and take the second course in this series?
No, I don't.
Okay, I didn't figure so, but go ahead.
Would Pat be physics 2?
Yes. Mm-hmm.
Yeah. I'll have to take it.
Okay.
Next year, I think. But
next year. Okay. It's hard for me to gauge exactly how much interest usually goes into, or need, I suppose maybe a better word, into taking physics 2, and for those that are doing the algebra based. Reason being is I'm not as familiar with that area as the other. A lot of times if people have to take the calculus based physics for part 1, they'll usually end up having to take it for part 2. I don't know if the same thing holds true for the algebra based. So I didn't figure there would be as much of a demand, but I could be wrong. So trying to figure that one out as I go along. Okay, so we've already kind of talked about conservation of energy here. So when only conservative forces act on an object, the total mechanical energy is going to be constant. In other words, the kinetic plus the potential at the beginning is going to be the same as what you have at the end. Your potential energy may be either gravitational, it could be elastic, it could be both. If some forces are non-conservative, then we're going to label them as other. And the change in total energy of an object during an motion is equal to the work, other, done by non-conservative forces. So in other words, we're kind of adding in an extra element here. We've got our conservative forces and the energy that's related with them over here. And then we have the non-conservative forces over here. So when this happens, we account for that by putting this term right here. Now, one example of a non-conservative force is going to be a friction force. The reason a friction force is considered to be non-conservative is because it is also considered to be path dependent. The amount of friction that you would have scraping an object across the floor is going to depend on where you push it across the floor, right? So because of that, the amount of force that the friction is going to exert on the box is going to depend on where you push it along the floor. So it's path dependent. There are a few other forces like that. Drag force is another one, where if you've got an object that's falling through the sky, you know, it's going to depend on its path. Where does it fall? So that's going to have to be considered here. This graphic right here shows an object that's being thrown up here, where it starts with an initial velocity and then ends with a final velocity here that's 0. Here, whenever it's first released, it's going to have all kinetic energy. I guess this is a beaker or something. Here, you're going to have a mix. And then up here, it's going to be all gravitational because it's no longer moving. All right, so this is just basically a rehash of what we've seen, is that the work done on an object is going to be a change in its kinetic energy. The gravitational work that is being done is a component of that. This can be modeled by the change in the gravitational kinetic potential energy, which obviously is going to have a negative on it. The elastic is going to be following the same pattern. And then when you substitute all of this in, you get, well, basically a big mess. The one component we haven't talked about over here is this W other. We did mention it in the summary of this section. So for any process, the total final mechanical energy of a system equals the total amount of mechanical energy initially plus the work done by forces other than gravitational or elastic. I got a few problems to go through there. So how do we describe this work that's done by non-conservative forces? We take the final kinetic energy plus the final gravitational and elastic potential energies and subtract out what we had initially for all of those cases. Whatever the net balance is going to be, then that means if we have something that's not zero, then we have some non-conservative forces acting on this particular object. If it is equal to zero, then we don't have any of that. So in the list of kinetic and potential energies in step 3, you should include both gravitational and elastic potential energies when appropriate. And remember that every force that does work must be represented either in U or in W other, but never in both places. Don't double count. The work done by the gravitational and elastic forces is accounted for by the potential energies. The work of the other forces has to be included separately. So you can see here the work done by the gravitational force is going to be the same for all 3 of these paths, whether they go this way, whether they go that way, or whether they go this way. And the reason is because the initial position and the final position are the only things that matter. A force that permits two-way conversion between kinetic and potential energies is going to be called a conservative force. And the work of a conservative force is always considered to be reversible. Anything that we deposit in the energy bank can later be withdrawn. So work done by a conservative force has these properties. It can always be expressed as the difference between the initial and final values of a potential energy function. It is reversible. It is independent of the path of the object and depends only on the starting and ending points. And when the starting and ending points are the same, the total amount of work is zero. It may not seem like that, but that is in fact how it works. When all of the work done on an object is done by conservative forces, the total mechanical energy stays the same. In other words, you haven't lost energy within that system. Other non-conservative forces can be tension forces or applied forces and can actually add mechanical energy as well as take it away. That's always something you have to watch out for. All right, last section here. Why did I click on that before I talked about it? Let's see. It's going to be power. How do we define power? Basically, the power is going to be defined as how much work can be done by something over a certain amount of time. Another way to look at that is the change in work over the change in time. Power is also going to be defined as the force that is moving in the parallel direction of the object along with its velocity. So that product there is going to define power. So I don't know if you've run across limits, but if we were to look at instantaneous work, then we're going to take the average power in that limit and we're going to take time down to 0. Instantaneous power can also be written as the product of the component of the force along the direction of motion and the speed of the object. The units of power, or average power, is going to be energy per second, so joules per second. Again, it's not a vector. It can be positive, negative, or 0. Power is not going to be the same as energy. Power is a measure of how much energy you can apply to something over a given amount of time. So we've got a picture here of work on a molecular scale. Be kind of interesting. Instantaneous power, again, is the limit as delta T approaches 0 of this expression. Power is measured in kilowatts or megawatts. In the British system, it is expressed as foot-pounds. And the unit of power is going to be the foot-pound per second. A larger unit is going to be called horsepower. This is a definition of horsepower. 550 foot-pounds per second is equal to this crazy little unit there. And you can see the relationship here between horsepower and kilowatts. The watt is going to be a familiar unit of electric power. You'll see that in light bulbs, where it takes a certain amount of electrical energy to turn it into light, heat. But the watt is really not necessarily confined to electricity. A light bulb could be rated in horsepower, and some automobile manufacturers rate their engines in kilowatts as well as horsepower. So there are units that are interchangeable, although in some contexts, you may see references to one unit more than you would the other. So the kilowatt hour, which if you pay your electric bill, you'll be somewhat familiar with. That is your usual commercial unit of electrical energy. And it changes from kilowatt hour to 3.6 megajoules. And the kilowatt hour is going to be a unit of work or energy, not power. So when a force acts on a moving object, it does work on the object. Corresponding power can be expressed in terms of force and velocity. So suppose a force acts on an object while it undergoes a vector displacement. If you can catch what's parallel, what force is parallel to that velocity, this is what you come up with. If you want to do it instantaneously, you take the limit as delta T approaches 0. And although energy is an abstract physical quantity, it is actually bought and sold. You can go out there, and there is such a thing as energy futures. I don't recommend you mess around with them unless you know what you're doing, but yes, you can trade those. Several examples there and a summary. Okay, that is a brief nutshell here of chapter 7. Obviously, you've got problems that you'll need to work with, and I think as you work the problems that the concepts will become clearer, and that's generally true of any chapter. Any questions up to this point? I know that's a lot to throw at you, but just want to check and see if there's anything glaring here that I need to go over.
Nope, I'm good.
Okay. Okay. Well, that's what I've got for tonight. I promise I will get the next lab lecture and video out here. I've got a little behind on that, so I'm hoping to get that done this weekend. Other than that, just keep doing what you're doing. I'm happy you guys are aboard.
Thank you. Have a nice night.
All right, you do the same.